Today we are going to discuss about the diffraction of light. Diffraction phenomena is exhibited by anything which has got wave nature. It is exhibited by sound wave, it is exhibited by light wave, it is exhibited by X-rays. All such waves exhibit this phenomena of diffraction. What happens actually in diffraction? If the wave is incident on an obstacle whose dimension be comparable to the wavelength of incident wave, the wave bends round the corner of the obstacle. You can observe we have taken a source of light wave, and this is an opaque obstacle. Wavefront from the light wave strikes the obstacle. We have the screen here. If you go by rectilinear propagation of light, we shouldn't observe illumination in this region below the central point on the screen. But we do the intuition of light wave in this region. This could be due to the bending of light at this point and has been shown here. Now, it's not that any obstacle will produce diffraction. We should have the dimension of the obstacle comparable to the wavelength of wave. For example, sound waves are diffracted by the obstacles of the sizes of say double-story buildings also, where the wavelength of sound wave ranges between a few centimeters to few meters. Light waves have the wavelength ranging from a fraction of micrometer to micrometer, and therefore the obstacle which has the same dimension, say the edge of the blade, can be used for the diffraction of light. You can actually observe the diffraction by making the pupil of your eye and looking at the bulb. You'll see the bright rings in the field of view. That is due to the diffraction of light. If you look at the X-rays, X-rays are also diffracted, but the X-rays are wavelength in the range of say 1 angstrom to 15 angstrom. So we should have the obstacle also of the same dimension. The crystal planes of the crystal, which have the same interacting spacing, do show the diffraction of X-rays. So, the primary condition for this phenomena to take place is that the dimension or the size of the obstacle should be comparable to the wavelength of the wave undergoing diffraction. Now, the classes of diffraction. Two basic classes of diffractions are Fresnel class and Fraunhofer class. In the Fresnel class of diffraction, the source and obstacle are at finite distances, as well as obstacle and the screen are at finite distances from each other, and no lenses or mirrors are actually used to produce and analyze this class of diffraction. In the Fraunhofer class, the two distances are infinitely large, and use of lenses and mirrors are made to make this. By keeping the source at the focus of the lens, you can have a parallel rays which are supposed to be coming from infinity, and in the same manner the diffracted beam can be brought to focus at any point on the screen with the help of the lens. Both Fresnel and Fraunhofer lived a very short life of about 34 to 35 years, but in this short period of time only they had earned their names. We will actually study today in detail Fraunhofer diffraction at single slit. We take the single slit here, AB, of width B. A plain monochromatic wavefront is incident on the slit. The waves are diffracted from the slit. Diffracted beams are brought to converge at any point on the screen with the help of the achromatic convergent lens system. Now, if you observe the point P on the screen, which is the central point with respect to the plane of the slit, the waves from all the points of the screen are reaching here, and if you observe the wave from the point A and point B will be covering same distances, the path difference is 0. This obviously will be the point of maxima or central maximum, we can say. And in this manner, the wave from all the points of the slit after diffraction reaching the point P will be in the same phase, will be producing central maxima therefore. To observe the position of first order minima, we imagine the slit to be divided into two equal halves, AO and OB, each equal to B by 2. And consider the waves diffracted in the direction theta from the direction of incident beam, which are brought to focus at any point P prime on the screen with the help of the convergent lens. Now, if you observe the points A and O being the midpoint of the slit, the waves diffracted from point A and O reaching the point P prime on the screen have a path difference of ON prime, which is equal to B by 2 sine theta, as this is B by 2 and this angle is theta. So it is equal to B by 2 sine theta. And if the path difference between the waves diffracted from A and O reaching the point P prime be lambda by 2, we will be getting the minima here, the first minimum. We can imagine a point just below A in the upper half of the slit and same distance below O in the lower half. The waves diffracted from these two pair of points will have the same phase path difference of B by 2 sine theta, and therefore they will also be producing minimum at the point P prime. And this way we will have the points in the upper half of the slit AO corresponding to which we will have the points in the lower half of the slit OB, such that the waves diffracted from the pair of points, corresponding pair of points, will be reaching point P prime to produce minima. And therefore, we can write for first order minima at P prime, B by 2 sine theta equals lambda by 2, and B sine theta is lambda, sine theta equals lambda by B. For small theta, we have sine theta equal to theta, so we have angular position of the first order minima we can get from here, theta equals lambda by B. And this will be on either side obviously of this central point P on the screen. Now, for first order minima, we imagine the same slit to be divided into 3 equal parts this time, such that the width of each part is B by 3 and the path difference between the waves diffracted in an arbitrary direction making angle theta with the direction of incident beam will be equal to B by 3 sine theta this time. And for minima at the point P prime, we should have B by 3 sine theta equals lambda by 2. Now, We can extend the similar logic, similar explanation that the waves diffracted from the different points in the first part of the slit and the corresponding points in the second part will be reaching point P prime and producing minima as the path difference is lambda by 2. So these two light waves from these two parts of the slit will be cancelling the effect of each other, but the third part remains uncancelled, which will give illumination. And therefore we will have first minima, but it's obvious that the width of the slit has now become this time one-third compared to the central maxima, and therefore the illumination of the first order maxima will be very less in comparison to central maxima. We observe this here. The angular position of the first order minima is given by sin theta equals 3 by 2 lambda by b. And it's clear now if we draw the intensity diagram, intensity versus angular position diagram. We observe this is the central maxima. You can see lambda by b on this side as well as on this side. You can see here. So the angular width of the central maxima will be 2 lambda by b. And if the focal length of the lens, which is kept very close to the plane of the slit, be f, the width of the central maximum will be equal to 2 lambda by b times f. This is the width of the central maximum. Similarly, the width of the central minimum will be lambda by b times f, and so on. What we observe, unlike interference, we have the fringes here of varying intensity. The central maxima is very bright, but the brightness goes on decreasing with increasing order of fringe. This is obvious because you can see the central maxima we observe by the diffraction from the entire slit, whereas the first order maxima we get due to the diffraction from 1/3 part of the slit. The second order maxima similarly will be getting from 1/5 part of the slit, and this causes a decrease in the intensity of the beam because the intensity of the pattern at the screen is directly proportional to the width of the slit, which causes diffraction. Now, it's clear that the width of the central maximum is proportional to the wavelength, waves used, and it's inversely proportional to the slit width. And the width of the slit is increased. If the width of the slit is increased, the fringe width decreases gradually and it becomes indistinguishable. And therefore, you can see only up to second order or third order maxima at most in diffraction pattern, whereas in interference pattern you see the large number of maxima and minima in the fringe pattern. Now, to obtain the distribution of intensity in the diffraction pattern, we make use of superposition principle. In the superposition principle, as there are a large number of waves, each of same amplitude and a successively increasing phase difference, phase of lambda and delta, we can use this superposition principle to find the resultant intensity of the wave. The first one being this A, the second one having A cos delta. Delta is the phase difference whose horizontal component is A cos delta. The vertical component is A sin delta. The third one we have A cos delta, A sin 2 delta, and therefore the sum of the horizontal component will be given by this, R cos phi equals this, and R sin phi, which is the sum of the vertical component, will be given by this. The resultant amplitude, after a bit of mathematical calculation using a bit of trigonometry, we can find to be equal to Na sin alpha by alpha, where alpha equals N delta by 2. Delta we know in the beginning we have seen that is the phase difference between two consecutive waves. And this we can take to be A sin alpha by alpha, where A equals N times A, and that since intensity at any point is directly proportional to the square of the amplitude, and therefore we should have I equals R square. This gives you the intensity. I for A square we can use I naught, and intensity of maxima and minima in the diffraction pattern on the screen can be obtained using this concept or this relation. So this is all about. You are free to ask any question once it is uploaded. You are free to ask question related to this. Thank you.